if anybody have any issues or any query, we can take during the talk also. Okay. What I did actually in this particular talk, I try to make it as simple as so that it can be more acceptable or understandable. I have taken some very simple examples from the maybe chemical engineering problems. I didn't took actually the big problem of chemical engineering, or I didn't go for to the definition of the chemical engineering problem. I had taken the reduced form of the problem actually. So basically, whatever you will see, the reduced data is there, or reduced form of the problem is there, and then we will just try to analyze the data with the help of linear regressions or polynomial interpolations. So what are different techniques we are going to discuss in this particular course? Okay, if okay, let me start with this thing. So what I'm going to deal with this in this talk is I'm going to talk about linear regressions. What are different scenarios during linear regressions actually? That will I'll talk linearization of nonlinear equations, polynomial approximation using different methodology like Newton's interpolation and Lagrange interpolation. Okay, so the thing is, I'm not going too much deep of all these methods. What I'm going to follow is more understandable form, so that we can understand what is this method and how we can apply this method. I will take the help of Microsoft Excel, because so it will help me to do the fast calculation, so it can be seen how the method work. Okay. In fact, if you see MATLAB also have they have introduced some kind of app actually, regression or curve fitting app. I mean, we can straightforward directly use that app for our curve fitting. Okay, but the problem happens that we know that there are different tools are there. We know that there are different tools are there to make a model. For example, if I have this particular data from some wind tunnel data, actually I have taken this data. Let's say there is some wind tunnel is there, and in this wind tunnel some object is falling down in the downward direction, and so what is being done at different velocities, some force values are being measured. At different velocities, some force values are being measured, and I just wanted to fit this data. Okay, as a beginner actually, I mean as a beginner, or let's say, let me go back to the undergraduate experimental lab. What people do typically, I tell you, I mean let's say mass transfer lab, what we do in the mass transfer laboratory and all. What the student does, they take the temperature data versus concentration data, and thus this data is simply being they see, and when we say that let's fit this data, what typically people do, they make a line passing through in between the data actually, arbitrarily. Let's say, I mean, there are n number of groups are there in the laboratory, and n number of the people have done these experiments. These n groups have done these experiments. So n groups have different these lines actually. I mean, somebody will do line like this. Somebody will do like, I just heard. So somebody will come with this line. So nobody will have this kind of a proper pattern actually. So what actually line should be? What should be the model actually? Some people will come with some model, some people, I mean some model and they just simply take the slope and then take the intercept of this line and then come with some kind of, somebody will come like here and this have some different slope. I mean, so there is basically some data are available, people will come with different scenarios. That is not acceptable. That's what typically people do in most of the time. I mean, they simply plot the data in the graph and then just come with this kind. Other thing what people do, I mean more smarter people actually, what they do actually, they go to the Microsoft Excel, fill all these values. So for example, if I just go back here, I'll just they just simply take this data, and then I hope my Microsoft Excel is visible to all of you.
Yes, yes,
Okay, perfectly.
it's good.
Okay. So, and most of the people just simply take this data, plot in the Microsoft Excel, and then just put some this trend line or maybe this linear with display equation chart, display R square value. Okay, and this and the people will just come with this kind of thing. Now, my question here is that how in this how this value is coming, how this value arise, and what is this R square here actually? What is this R square in this thing? Okay, and how this R square is being calculated? How this equation was developed? Maybe one group will come this linear fitting, other group will come with other scenario. If you see this another group will come again at trend line and then the polynomial of let's say 2 degree, that's a quadratic polynomial with this equation and this. So another group has come with this kind of this. Okay, now if people know that, because if the high R square value more close to 1, that is best fit. For example, in this case, how it is coming, R square is coming like R square is coming with the linear fitting 0.887, but with the quadratic fitting it is coming 0.9569. So that means this is good one. But again, my question is how this R square, what is the significance of this R square, how it is being estimated, how these values are being calculated. This is the thing actually which we need to understand. Otherwise, sometimes we just do the fitting and then without knowing that what it is suggesting, then we just simply report the model. Maybe there are some other ways to go for the better model of this data point. Okay, so that way actually, I mean, we need what my approach here is, how what may be different scenarios, how we can solve the different data points, how we can linearly means regress those data points for different calculations and all. So here this I mean with this particular example I'll try to demonstrate how this modeling of the data is being carried out. Okay, now there's other kind of people are there. I mean, how they do this analysis actually, very crude way of modeling. Let's say some further smarter people are there and they are come up with some other methodology of the modeling. Okay, let's say I give this data point to some students or somebody actually, and then I ask them find the value of force at velocity is equal to 2 meter per second, 3 meter per second, or 4 meter per second. Okay, I ask them value what is the force value at velocity 2 meter per second, 3 meter per second, and 4 meter per second. How should I get that value? Okay, so if some people have some basic knowledge about the regression analysis and all those things, they first try to go with the very crude way of doing this analysis. What they do actually, because I ask 2, 3, and 4, so they will select only these 4 data points, because we are not going further four actually. So select 4 data points. If I'm selecting 4 data points, I can make a polynomial of degree 3. If I'm selecting 5 data point, then the polynomial of degree 4. If I'm selecting 3 data points, polynomial degree 2. So that way actually we work. So let's say, we have selected these 4 data points here and then proposed a polynomial of the 3 degree. Fx is equal to ax cube plus bx squared plus cx plus d. Now let's say just putting the value of x into this particular equation which we have taken, polynomial degree 3. Let's put x is equal to 1. I came up with this equation. Okay, then is equal to force, f of x, that is force actually. Then again I put x equal to 2.7, x equal to 3.2, x equal to 4.1. Okay, so when I have this polynomial. I had assumed this polynomial which are having unknowns a, b, c, and d, and then putting all those values of x on which I am calculating developing the polynomial. Actually, I'll have these four equations. I'm sorry. So now when I'm just trying to solve these four equations, I'm just trying to solve this four algebraic, polynomial equations. There is a different ways actually. First approach is what I can do simply. I can write, because I've taken four data points. So I just write four polynomial equations like this, and I just simply convert this equation into a matrix form, because four equations I am having, just like equation 1, equation 2, equation 1, equation 2, equation 3, and equation 4. Okay, so now when I'm doing this, sorry, I'll just go back. Yeah, I came up with this kind of matrix. This is this x cube. You see this x cube, x squared, x, and here 1 actually. So x cube, x squared, x, and 1 for the first equation into a, b, c, d. So ax cube, bx squared, cx, and d is equal to f1x. Similarly, for other equation, the equation 2, again I am having same way. So I have converted this whole system, whatever I just mentioned above, into a the matrix form. So let's say these x cube, x square, x, and all are known to me, because I am putting x values here 1, 2.7, 3.2, and 4.1. So in each row, in this particular row, I'll put, it is shown here already. 1 in the first row, 1 in the second row, 2.7 in the third row, 3.2 cube in the fourth row, 4.1 cube. This, let's say these all are my solution vectors A, B, C, D, which I am determining so that I can complete my polynomial equation. And this is my right hand side vector. Let's say this is some, I'll just put some is equal to f, something like that. Okay, so what I am having, I have a matrix A x is equal to f. I simply do x is equal to A inverse into f, and I can get the solution vector A, B, C, D. And then once I get the values of A, B, C, D, after solving this matrix system, I will get these values of A, B, C, D here, and then putting back all those into this function f of x is equal to P for polynomial. In this expression, P for polynomial, 3 for degree, polynomial of degree 3 with base x is equal to, this is my A, if you see this one is A, x cube plus bx square minus cx, and this plus d. So I obtain this polynomial. So my aim was to first to develop the polynomial and then estimate the value of that function at the value of 3, velocity 3. Okay, so let me put x equal to 3. I'll obtain the values 20.212. If I'll go back to my data here, so if I say 3 at 3, it is coming 20.212. So basically, it is coming in between 17.8 and 22. That means it is basically following a trend. Okay, this way it is good. It has been done a very fantastic job, and we are able to develop a polynomial. We are able to calculate the value of force at a particular velocity. Okay, but this crude way of doing this polynomial development or model development is not preferable. It is not considered. Basically, there are different reasons are there. First reason is, if you see, we have taken this x, we have assumed a polynomial of ax cube, bx squared, the ax cube, bx squared, cx, and d plus d. Okay, now here it is coming x cube, x squared, x, and 1. If I'm writing the matrix form here, you can see x cube, x squared, x, and 1. Okay, now let's say my x value here is, instead of 1, 2, 3, 4, 5, it is like 10, 20, 50, 100. 10, 20, 50, 100. What may be happening due to that? If let's say x equal to 100, if I'm putting, okay, x equal to 100, I'm putting, let's say, or let me do it like this. X is equal to 10, 20, 50 and 100, corresponding force value, whatever the force value I am having. Okay, so what it will happen here, this will be 10 cube. So 10 cube will be like 1000, 100, 10 and 1. This will be like this will be 400. Sorry, 4000, 4400. Then and this is 20 and 1 and 50 becomes 250, 00 and 25. Okay, then again
Yeah,
125.
it would change actually something.
Yes,
Something 8,000 8,000 at first because we are cubing,
8,000.
right?
Yes, 8,000. Yes,
Uh, uh,
8,000.
uh, uh.
8,000. This is 125,000.
Yes,
This
yes.
is 2500. This is 50. This is 1 and this is 10 lakh. 1, 2, 3, 4, 5, 10 lakh. And then this is 10,000. This is 100. This is 1. Now see this. This is a bad matrix. Why we are saying this is bad matrix? One of the value is 10 lakh. Other value is 1. If one of the value is 10 lakh and the value is 1, this matrix we are referred as ill-conditioned matrix. Ill-conditioned matrix means one value is of the order of 10 lakhs of the other value. I mean, so that what will the consequence of that? If you are calculating A inverse, it is not calculated. I mean, we cannot go for the calculation. This value will be too less or maybe too high as compared to the other. This is not a preferable thing actually. A inverse value will be very haphazard value will obtain. Okay, when I said ill-conditioned matrix, actually ill-conditioned matrix we are referring when one of the value is too small as compared to the other values, or one of the values too higher as compared to the other value. How do we estimate condition number? Condition number simply estimate is like condition number is equal to
Excuse
norm
me,
of.
sir.
Yes,
Yeah, I want to ask here something.
yes,
So suppose we got a matrix
yes,
and let's say somehow a person has calculated inverse.
yes.
Somehow he has calculated inverse. So if the inverse is calculated, again those calculated function would not perform well, or it would ill-conditioned thing would create problem only to finding inverse only.
Actually, determinant will approach near to zero actually in this scenario when we are dealing
So
with.
he would face the problem in getting the means the inverse of the matrix.
Yeah, it is difficult to get the inverse of the matrix in that scenario
So
because
if the
determinant
somehow,
is very, very small. Very, very
yeah, yeah.
small.
So if the somehow person can get the inverse of the matrix or can somehow change this solution of the matrix technique, maybe he can
Yes,
make it
yes, yes.
diagonally to a dominant
If
and
we are
then
able
he
to
can solve.
change the solution of this kind of, there is a, when we deal with the linear algebraic equation actually,
Yes, yes, yes,
their
exactly.
methods are there to solve such kind of scenarios. They
Yeah,
are,
to make them diagonally dominate
but
something and then solve
but
it.
the focus is not in the present talk. My focus was not to deal with it too much with the matrices, rather
Yeah,
talk about the regression kind of thing actually.
correct, correct.
Okay, so
Okay,
but
okay,
the
sir, go
thing
ahead.
is their methods are there which can
Hmm.
be helpful to do the calculations for this
Such type of matrix.
ill-conditioned matrix. The methods are there. Methods are
Okay,
obviously there. Okay,
okay,
so
sir.
okay, let me go. So what I was talking about, A inverse value is very difficult to get, or it's a very haphazard value actually. So this is being the whether a matrix is ill conditioned or well conditioned. How do we determine that? We determine with the help of condition number. Condition number is nothing but norm of a matrix A divided by norm of matrix A inverse. Okay, so from that we obtain, for example, this scenario. We have a 4 by 4 matrix. Okay, so that is for cubic polynomial. Cubic polynomials. Okay, for this, and this condition number is approximately 2700. Okay, if I'm taking a 5 by 5 matrix, 5 by 5, that means we are having a fourth degree of 4 degree of not fourth 4 degree of polynomial. So in that case, my condition number was coming 62,000 actually. So condition number is increasing because A inverse value is getting decreased. The norm of A inverse is getting low. So in that case, this is not preferable because condition number desired is as less as possible. The smaller the condition number, my matrix is well conditioned. Larger the condition number, my matrix is ill conditioned. I should not go for it. So this is the one of the scenario with this kind of matrix formation. Other scenario is, let's say if my matrix size is increasing. In this case, matrix size was 4 into 4, 5 into 5, or let's say I go for 6 by 6. As my matrix size is increasing, my determinant of my matrix will tends to 0 actually. 0 tends not exactly 0, but it will tends towards 0. So that is again a problematic in this kind of crude way of doing regression analysis. Developing a polynomial. That's why this method is not preferable for developing a model for regression for a particular system of data points which are available to us. Okay, so we had started with this particular simple example. Other thing is, let's say I developed this polynomial and I estimated the value for this function at 3. That means I'm doing interpolation. If I'm going for extrapolation, I obtain this value. This value is 45.14. If you see, if you go back to my experimental data, it is 51.7. If you see here, 51.7. So approximately 10 to 15% error is there in that. So we don't want that actually. Okay, so that will extrapolation. This method is completely false. Okay, and so this robust way of doing model development is not acceptable due to several reasons. So that's why we go for something like what we term as polynomial regression or polynomial regression. Okay, so I'll come on to this example later on. So first kind of polynomial regression we talk about least square curve fitting. Least square curve fitting. Why we are saying least square curve fitting? I'll try to answer later on. Let's say I'm having data point x0, y0, x1, y1, x till xn, yn. Okay, and so that means I have 1 to n is n number of data point, and x0 is also there. So n plus 1 set of n plus 1 data points actually I am having. Okay, now let's say these data point I wanted to fit with a linear regression or with a straight line. I want to do fitting of this data with a straight line. For a straight line, equation is y is equal to a0 plus a1x. Okay, so first thing what we do in this case actually, all these y0, y1, y2, yn are my experimental data points. This y is equal to a0 plus a1x is my that predicted. I'm developing a model. So model always gives the prediction. So predicted, or let's say calculated values actually. So when my calculated value will not be same as the experimental data point. Okay, so basically there will always be a deviation between the experimental and the calculated values. And when I propose this model y is equal to a0 plus a1x, I don't know the value of a0 and a1x. So how do I find those values of a0 and a1? Okay, let me come back to this one, my Excel sheet actually. Here, if I talk about, let me just remove everything from this here. I'll just remove this one. Yeah. So when I did this linear regression of this data point, I obtained this particular equation. So here a1, this is my a1, this is my a0 actually. Okay, so how do we obtain this value? Excel has already inbuilt function into it, but we must know how it is being done. Okay, so for that, how do we proceed? The deviation, we take the deviation between the available data points, that is all the y's, and the calculated data points. So that is yi minus a0 plus a1 xi, where I varies from 0 to n. Okay, so this difference between, or the deviation between these data points, the yi minus a0 plus a1 xi is nothing but we refer as residual. This is error or the residual actually. We refer it as residual. Okay, so now let's say, can we get my values of, the correct model with this equation or not? Can we get the correct model from this equation or not actually? Okay, so for that, if I proceed further, there are different best fit criteria I should look for. First is the same equation which I just shown you. This particular residual equation, E is equal to yi minus a0 plus a1x. Okay, so sorry, so a0 plus a1x. So what happened here, if you see, when I calculated this value, the first scenario I'm talking, first scenario, summation of yi minus a0 minus a1 xi. Basically, I open the bracket, so it is minus now. So in that first scenario, what happened? Let's say this straight line is representing my this data point. The black and the blue one are my data points, which I'm just simply connected with the help of the line. Simply not a fitted actually. When I'm fitting this kind of scenario, it will result into some kind of intersection at the midpoint of the equation kind of thing. Scenario will come, and this will also give some kind of positive and negative errors actually, which is not desirable. Or in other words, basically this equation of best fitting is inadequate criterion, because what happened, when this straight line passing through the midpoint or the connecting line, it results into a minimum value, okay, which is equal to 0. That may result in some kind of positive and negative kind of signs into it actually, into this. So this is first best fit is being avoided basically due to these reasons, because of signs. So second best fit is being approached by taking the modulus of residual. By taking the modulus of residual. Now we are taking modulus, that is absolute value. Okay, so again this let's say I have taken the modulus actually, but it will result in the spread of the data points with respect to the fitted value. With respect to fitted value, it will result into the the spread in the data points. So what we do actually, let me take the other approach, which we say that min-max approach actually. This is minimizing the maximum distance between the predicted value and the calculated value. So it will be something like, for some data points are very well lying on the curve, but there may be some kind of outliers are also there. If you are going to minimizing a distance between the experimental fitted data points, so their number of outliers are there. So to avoid this outlier, this third fitting also not min-max approach, which we say is not suitable here actually. Okay, so just to avoid that, because these outliers will influence the model and it will show that there is an error into the model actually. So this also not suitable actually. So all these three approaches are suitable. So what happened, if I go back to this equation, we take the least of sum of squares actually, sum of a square kind of approach. This ei square, I is equal to 0 to n, with summation I equal to 0 to n yi minus a0 plus a1 xi whole square, where SR is the sum of the square of the residuals. SR is the sum of the square of the residual. So basically using this expression, we try to fit the linear regression kind of thing. Okay, I taught the different best fit approach simply without square actually, first one. Okay, this results in some kind of plus error, minus error kind of sign error with the signs actually, that is not desired in any method. So we took the absolute, that also resulted into some kind of spread of data. Third one is the third one approach, which min-max approach related to some kind of outliers, that also not suitable. So we came with this the final one, the sum of the square of residuals. This will help us in minimizing the difference between the calculated and the predicted values, and then it will help us in calculating value of A0 and A1. Now, how do we get the value of A0 and A1? Simple. We differentiate this whole function first with A0 and then second with A1. So sum of the square of residual we differentiate with A0 and A1, we obtain these two expressions. So I'm not reading everything in this expression. And then because we are minimizing the error between the calculated and the predicted values, so we equate these functions equal to 0 and equal to 0. So let me do that here. So when I'm equating with the zeros, these two functions, I obtain this equation, this one, first equation and the second equation. Now I can solve this by two ways actually. I can simply rearrange both the equations and I can get the value of A0 and A1 from this. Or otherwise what I can do also, I can do like this. I can simply take out A0 and A1 and A0 and A1 are common. So just simply take out that common. So converting this algebraic equation into the matrix form. So like that, n plus 1, if you see here, n plus 1 sigma xi. So here I am having n plus 1 sigma xi. Similarly, second equation, sigma xi and sigma xi square. So sigma xi and sigma xi square, A0 into A1 is equal to sigma yi sigma xi yi actually. So that is right hand side. If you see here, this is sigma yi sigma xi yi. Okay, so that means I have converted that into matrix form. So let's say this is my coefficient matrix A, this is my solution vector A, and this is my right hand side vector B. A is equal to B, and or if I want this A0 and A1, A is equal to A inverse B. I can do that actually. Okay. Or by rearrangement method of this equation, whenever I'm rearranging these two particular equations, I obtain A1 is equal to n plus 1 sigma yi minus sigma yi divided by n plus 1 sigma xi square sigma minus sigma xi whole square, and A0 becomes minus 1 over n plus 1 A1 sigma xi minus sigma yi. Okay, so if I just take this 1 by n plus 1 here, actually here as well as here, so this will be like summation of all the data points, and total number of data points are n plus 1. So this is nothing but mean of x. This is sigma y over n plus 1 is nothing but mean of y. Okay, so y bar minus a1 x bar is will results into this equation. So this I can rewrite this whole expression, like y bar after rearranging is equal to a0 plus a1 x bar. If you see, this equation looks like y is equal to a0 plus a1 x. It looks like that actually, the same equation which I was talking about. Okay, so let's say yeah, so now once we have this means we have developed this equation. Sorry, it is gone. Yeah, when we have developed this equation, we got, we have got the a0 and a1, and if I just go back to this first equation here, this one, I will put the value of a0 here, a1 here. Okay, now I wanted to understand this equation, that what does it signifies actually. Okay, what does it signify? If I see sum of residuals, sum of square of residuals actually, yi minus a0 minus a1 xi. So I have all this value, I put into it. Okay, this is nothing but, if I just see this this expression also, a0 plus a1 x bar. Okay, so I can rewrite this expression like summation of yi minus y bar square. Okay, so this one is like if I plotting this is my experimental data, This one green point, if you see, is my experimental data. And if I'm just past, sorry, this is my experimental data. This is my experimental data. Okay, this is my regression line. This blue line is regression line, and this data corresponds to the regress or the predicted data, predicted value. So this is telling me that the deviation between the experimental and the predicted value is yi minus a0 minus a1 xi. Okay, this is telling me that the deviation is given by there is one thing actually. This is t. That's not actually. This is t. This is a different. This is SR. Sum of residual errors. Actually, this is total deviation from the data. Total deviation from the data. Actually, so there are two different definitions which we typically deal with the deviation in the experimental data, and one is with the actual equation, which was like y is equal to a0 plus a1x and yi, let's say ixi. So another one was like y bar is equal to a0 plus a1 x bar. This we obtained here. Okay, so here this is telling me the deviation between the experimental predicted value with respect to that sorry, between experimental and predicted values. Let's not going to it. So now when we typically define the standard error of the estimates, when we typically define the standard error of the estimate, how do we do that? We define there are different ways. One is, if you see, I have put like sy of x, another is simply sy. Sy is my standard deviation which I typically calculate. Okay, so when I'm calculating that, I have put here n minus 1. Actually, this was not n minus 1, it was like n plus 2. Sorry, this was n plus 1. Sorry, n plus 1, n plus 1 minus 2. Yes, n plus 1 minus 2, because this 2 is coming because there are 2 degree of freedom we are already reducing by taking a0 and a1. We are already reducing the 2 degree of freedom within the n number of data points. That's why this minus 2 has come. Or this minus n plus 1 is because I have n plus 1 data point. Okay, so that's why this n minus 1 is coming. So don't get confused with this, why the n minus 1 is there, because some people in some books and some references they will take like n minus 2. Instead of n minus 1, they take n minus 2. Okay, but here I have n plus 1 data point. So that's why n plus 1 minus 2, it is become n minus 1. Okay, so that way it is coming. So syx, we typically referred one way is spread around the regression line. Spread around the regression line is given by under root of SR over n minus 1. Okay, SR was, I told you, sum of square of residuals. Sum of square of residuals actually. Okay, and n minus 1, just like I told you, the number of degree of freedoms was n minus 2 actually. 2 minus 2, I told you, a0, a1 we already have predicted. That's why we are left with n minus 2 actually. So here this way sy of x is sr under root sr over n minus 1. Another is sy standard deviation. This is from this st over n. So st was sigma yi minus y bar over y square. So this is standard deviation we calculate, and then this one typically we represent in the form of variance in the data point. So that variance is nothing but square of sy. So simply taking the square of that term will be the variance actually. Okay, now coefficient of variation or coefficient of variance actually, with this how we define this coefficient of variance is like sy, that means what is the value, the standard deviation by the mean value. Standard deviation by the mean value. So these are the formulation, or all are drivable formulations. So I'm not going to detail derivation of those formulations. Okay, for this one. Okay, now further, I told you something like here r square. If you see here, r square is equal to 0.887. So what is r square actually? Okay, this r square is nothing but we take the difference between the total deviation or minus the the sum of square of residual sum of square of residuals, that at that or this difference will tell me the error reduction due to data in terms of straight line instead of an average value. So in terms of straight line, so error reduction in terms of straight line rather than an average value. Okay. Or maybe in very layman's way, I just simply take the difference between the total deviation minus the sum of square of residuals kind of thing. And because this is scale dependent means data dependence basically, so we just normalize this data with respect to the total deviation. So we have R square is defined between the difference between ST minus SI divided by ST, which is we refer to coefficient of determination. R square is coefficient of determination, or R taking the under root of R square is R is correlation coefficient. How do we obtain correlation coefficient? Is like R is equal to n plus 1 sigma xi sigma yi minus sigma xi sigma yi divided by under root n plus 1 sigma xi square minus sigma xi whole square into under root n plus 1 sigma y square minus sigma yi whole square. So this equation basically whatever you see R square value is being calculated with the help of this R and then the square this value. Okay. Or simply we can calculate the total deviation, we can calculate sum of square residuals and then normalize it and the total deviation. We can get the R square value from there because we already know these equations. These equations are here. SR is there, ST is there. We can calculate that actually. Okay, so we can calculate that. Okay, so once we have this, before that, let me demonstrate it here. Yeah. Let's say I have these data points. Velocity is 10, 20, 30, 40, 50, 60, 70 and 80 meter per second. And at different velocity, this object, let's say this is my some region from which this object is falling down at different velocity and we are measuring force. Okay, so when the object is falling down, it feels some kind of drag actually. It feels some drag, and so there is a relationship between F is equal to some drag coefficient into velocity to power, let's say A. Something this is a true relationship between the force and the velocity. Obviously, I can say from this data that with increase in velocity, force is increasing. But there is another parameter comes the drag coefficient because it means it feels some drag when it is falling down into the wind tunnel or some other region actually. But okay, but I don't know value of CD here. I don't know this value A. Okay, so how do we estimate that thing? So that will come with a fitting. So I will take this fitting of this using this expression later on. But what I do actually, let's try to fit this data linear regression. That means straight line. What will happen? Just a minute. What happened there? Yeah, here. Yeah, you can see this data point. All these data points are same. Okay, I just give some index number so that I equal to 0 to 0, 1, 2, 3 till 7. So total number of data points are 8 actually. Okay, so total number of data points are 8. Now if I go to, because I have to fit this value like this one actually. If you see this formulation is given here. Sorry, this formulation is given. Or I can say like that yi is equal to a0 plus a1 xi. Okay, so if I'm just fitting that, so I need to know value of a0 and a1. So when I need to know value of a0 and a1, if I go back here, yeah, a1, what I need, sigma yi into xi, one thing, sigma xi I need, sigma yi I need, sigma xi square I need, sigma xi whole square I need. Okay, so that sigma means summation of all the data points. Okay, so if I sum all these data points, I obtain this 360. So basically summation of xi is equal to 360, summation of yi is equal to 5135, and then I have summation of xi square. So this x square, I did the x 10 square, 20 square, 30 square till 80 square, and then sum all those values. I obtained 20400. Other thing I need is sigma xi whole square. That means 360 square. The 360 square is I have written somewhere or not. I have not written here, but it will like 360 square. Sorry, I'll rewrite over here. It is like 360 square. Okay, and then I need sigma xi into sigma yi. So I just simply multiply this value 360 into 5135. Other thing which I need is sigma xi yi. So that means what I have to do, I have to multiply x and y. X and y 250, 20 to 70, 1400, and then take the summation of that. So it is like 312850. So now I'll go back to my formulation. Here I'll put all the values into this. I'll obtain A1. You can see here A1. Similarly, my A0 was, if you remember, y bar minus A1 into x bar. Y bar was not this. This is my this 45. X bar is sorry. This one is my what? X bar. This one is my y bar actually. Okay. So using these two values of mean, I simply calculate, and the A1 I calculated easy. Once I have calculated this, I developed this function. So this is my values of that A0 and A1. So I have developed this function here. So once I have developed this function, I have, from this function I calculated values also. This is my all predicted values. So I can write here y predicted or y calculated value. Okay. This is my actual y value. This is my predicted value. Okay. So you can see that one is 25 and then minus 39.58. Okay. This is seriously showing a deviation. Okay. Now here, if I just wanted to calculate what is my R square value, what is my R square value? So it is like 38053. I mean, I have to calculate like one is y minus y bar, that is ST. This is my ST, and another is SR. Using those two formulation, I calculate ST and SR. Once I calculate ST and SR here, so I calculated SYX using that ST and SR. And then ST and SI again, ST minus SR divided by ST, I obtain this one, R square here. This is showing like 0.8805. Okay. If I go back to this function actually, let me just put a this train this one straight line here, a train line. This one. You see this data point actually. This is A0 is minus 234.29. This is what Excel is doing, minus 234.29. This is minus 234.29. Okay. A1 is 19.47. A1 is 19.47. I mean, those data with R square is 0.8805. So simply when I'm calculating all these values with the formulation, it is 0.8805. So basically, R square value is telling me that what kind of fitting. I mean, you can see only the third and fourth data points are giving a very good fit. So third data point is this one actually, the 380, 350, 550, 550 approximately. So the otherwise all the data are not matching at all. Okay, so that means this linear, proceeding with the straight line is not a good idea. So what should we do? We just go for other equation. Instead of a straight line, let's say we assume a function like y is equal to b0 into exponential b1x. Other function. This is something like an exponential function, I assume. Okay, for the same data, exponential function. How do I solve this? This is a non-linear equation. How do I solve this? I simply linearize this equation using log, taking log of both sides. So log y, log b0 plus b1x into log e. Okay, so b1x will come here, log e will be there. So log e, we know it's 1. So why reduce this form like log y log b0 plus b1x, simply. Okay, now this equation is log y. Let's say I just simply put y, log b0 is some b0, b1 is as it is b1, and x is also as it is x. Okay, but just for to make the similarity, I just put all capitals. Otherwise b1 and x are not different, rather y and b0 had changed. Now I'll fit the same way, the way I did in the previous this one actually. This calculation, whatever the calculation I did for a1 and a0, I will fit the same way here and get the values of b0, b1, and then I can put back into this expression here. So this is b1. Okay, this is y. So if I take the anti-log of b1, 10 to power b1, it will be like b0 actually. Okay, so that way I can then do the reverse calculation for that, and then I can get the b0 value. Okay, so let's say this was exponential function. Let me go back to my example. Let's say I told you that that particular example was like force is equal to some drag coefficient into velocity to power some a. Let's say this drag coefficient is alpha and this a is some beta actually. Okay, so this is my power law fitting actually, because we have taken some kind of equation in terms of powers actually. Now here I have to do this analysis. Log y, again I take the log both side, log y, log alpha plus beta into log x, and then writing this equation to general equation like y is equal to this become y. Let's say I'm just assuming y actually, just to make the similarity between the previous text actually. Log alpha becomes a0, beta becomes a1 x. So this equation is same as the previous equation. Okay, if I go back to this example, here we had assumed y is equal to a0 plus a1x, this one. So I have reduced a power law equation into the linear form by linearization process. So let me demonstrate that also to you people. If you see here, I have this x, y, I have simply taken log of x, log of y. Then I have taken log of x square and log of xi, log of y actually, so that I can put all the values. I have taken the summation of x. This is not needed in the present case actually. This is not needed in the present case. Rather, I need summation of log of x, summation of log of y. Then I also need the mean of this one. This one will be now my x bar. This one will be now my y bar. Log of x square, log of x into log of y. So basically I'm using the same equation now, this equation. So when I'm doing this, I have solved for this, I obtain a1 and a0 values. When I do this a1 and a0 values, I obtain minus 0.56203. I mean, this is after calculation. I have put the formula, so I have to minus 0.56 plus 1.98418x. And you know that this is the logarithmic form. I have to write into the actual form. So it will be like, if I'll rewrite it here, y is equal to, I have to take the anti-log of this value. If I'm taking anti-log of this value, this is like 10 to power minus 5, 0.56203. Okay, and x to power it is 1.98418. So this anti-log becomes this equation like y is equal to 0.27414 x to power 1.98418, or I can write like force is equal to drag coefficient into velocity to power 1.98 or 2 approximately. I can just simply write 2 also here. So drag coefficient I calculated by fitting this data like 0.2741. Okay, so this one, if I go back to this this chart actually, and if I do this power law fitting at trend line, then power law fitting, just putting this to equation, you can see it. Y is equal to 0.2741, x to power 1.9842, with r square value is 0.9481. It has been improved. R square value has been improved. So that means power law fitting is better than the straight line fitting for this particular case. Okay, so this way basically we deal with the non-linear equations or power law equation exponential formulation, and we get the values of a1 a0, and then we put into the formula back and we can write into the actual power law form that equation. Okay, now
Excuse me,
let's
sir.
take, yes please.
But can it be possible to change the powers actually? So we can also means play with the power of
Well,
the
change in the power
exponents,
means you are talking about the value of a.
second order polynomial.
You are
No, no,
talking
x
about y
square
is
thing.
equal to
So currently
a0
got
plus a1x plus a2x square, like this.
no, 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 no. I'm just taking the logarithmic fit, and I just want to play with the power of x only.
You wanted to this thing. I mean that y is equal to alpha x to power beta. So you wanted to play with the
Yeah, yeah, yeah. Yes, yes, yes,
that is
exactly.
the case where you have to go for optimization. You cannot use linear
Yeah,
regression.
yeah,
You cannot
yeah.
do linear regression.
Linear thing be yeah, yeah. That we cannot do.
I'll tell
I
you. I
can.
just kept one slide there actually. I kept for this
Okay.
also. I'll just
Sure,
come.
sure, sure.
Okay.
Okay, okay.
So here, okay. So here, let's say I have another scenario. Okay. I have carried out some reaction in a reactor. I have measured concentration. Okay. Concentration. That concentration is a function of time, pH, and temperature. Let's say I'm assuming. Okay. It may not be correct actually, but concentration is a function of time, pH, and temperature. So there are three independent variables: x10, x0, xn0. In the previous case, I was having only one that independent variable, one dependent variable. Okay, so y0 was, I'm predicting a concentration in a reactor, which is a function of temperature, pH, and T. Okay, I'll show you one example for this also. So how do I fit this data? How do I fit this data? Okay, what I do actually, for this all these data points, y0 corresponds to x10, x20, xn0, y1 corresponds to x11, x21, xn1, and so on. Yn corresponds to xn, x1n, x2n, and xnn. So I have the complete set of data points with y is equal to a0 plus a1 x1, so plus a2 x2 till so on till a and xn. That means I have a number of x values. It can be some other values of concentration may also vary with some other value also. Okay, so I make a very generalized function. Y is equal to a0 plus a1x. A0 a1x is only for a linear, plus a2x2. I again add one more point, plus a3x3 plus and so on till a and xn. Okay, I'll follow same method what I did for the linear fitting. SR is equal to that, again sum of residual square is equal to E was the residual, yi, that is this value, yi all are these values, minus this formula which I just calculated, formula, this formula. Okay, so all this formula I put here, and then differentiate this is, sorry, SR, I just by mistake I forgot to remove this SR. So DSR over DA0. So basically differentiating this SR, sum of square residuals, and differentiating first with A0, I obtain this equation, then with A1, then with A2, and then finally with AN. So I'll obtain n number of equations. I obtain n number of equations. Okay, when I obtain n number of equations, I'll again rearrange into this matrix form. Like again, just this is same thing which I did in the previous case or linear equation case also. So n plus 1 sigma x1i, sigma x2i, sigma xni, x1i sigma x1i, x sigma x1i, so into 1i. I mean this kind of pattern will come, and a0 a1 a this is like aj. Okay, this is aj, this is an. Okay, so this way actually we have made this matrix form. So I have a coefficient matrix, I have a solution vector, and I have a right hand side vector, and then I'm solving this equation, maybe taking the inverse of a, actually inverse of a. Okay, but the problem here is, I told you in the beginning, if my n is more than 6 actually. My determinant of a will tends to 0, so I should not go for very high number of I mean this the method more than 6 independent variable kind of thing actually. Okay, okay, I should not go for that. This in this scenario, so I can solve that equation. Then again, this this is nothing but my r square value, r value actually. This is r value. I again calculate for this particular data points where I am having n number of independent variables. Okay, this is one scenario. Let me show you if I'm having this here. Yeah, sorry. This is a typical example: gas transfer in natural water such as rivers, lakes, and estuaries. Gas transfer from the atmosphere, you can say that. It has been found that the mass transfer coefficient of dissolved oxygen, that is Kl, meters per day. I mean, what is that is a unit of that mass transfer coefficient. Is related to a river's mean water velocity. So what this river is going in some particular direction, so it is related to that mean water velocity and depth of the river h. This is given by this equation. Kl is equal to a0 u a1 h to power a2. So Kl is my mass transfer coefficient, u is the river velocity, h is the river depth. A0, a1 and a2 I make it like, I assume it is like a some kind of power law kind of function actually. Okay, power law function. And this we had measured these data points for u and h. Okay, so let's say this is x1 I, this is x xi1, let's say xi2. Okay, so basically I can also write like maybe simply x1 and x2 kind of thing. So x11, x12, x10, x11, x12, x13 so on, x20, x22, x33, sorry, x20, 21, 22, 23, 24 and so on. And then a different depth as well different velocity Kl value has been measured with the help of mass transfer probe. What I do in this case, I take simply log of Kl is equal to log of a0 plus a1 log of u plus a2 log of h. Yes, somebody was saying something. Okay, let's say I rearrange this equation like y is equal to, yeah, I have written here actually, I forgot to see it. Log of k. So I am rewriting this equation like y is equal to b0 plus a1x1 plus a2x2, and then taking sum of residual of squares. Okay, so that is by like this value, and then this sum of residual square I am doing like dsr over db0, dsr over da1, dsr over da2, and then again using this this kind of matrix form, this kind of matrix form, and then solving for this one b0, a1 and a2. Let's say these values I have obtained. Okay, let me see if I've
So at
taken.
last, are you making this derivative with respect to a1, a2, 0, right?
Yes. You see this b0, a1 and a2. This thing.
Yeah. So
Okay.
this DSR upon D A1
B,
it would be equal to 0 and all this would be equal.
yes, would be equal to 0. This is equal to 0. This is equal to 0. This is equal to 0. Okay. So then we obtain these values of b0, a1 and a2. Then I am putting back into this equation. Log KL is equal to b0 is 0.57627. You can see here 1.562 is a1 and a2 is 0.50742. And then taking the anti-log if I need it for that. Take the anti-log of that whole equation, and then I obtain the final equation of the form this. KL is equal to 3.7694, U 1.562, H to power 0.5074. So basically, we have taken the anti-log of this one B0 because that is only this equal to B0 equal to log A0. So taking the anti-log of that, we obtain this expression with sum of residual square this value and r square, which is the important thing. R square is 0.99619. I told you r square is close to 1 is what is desirable in any fitting, in any linear regression fitting. We obtained this R square is equal to 0.99619. So this way actually we can apply this linear regression analysis for any particular data point. Okay. Now let me have just what happened here. Yeah, here we have a scenario now. This is a different scenario. Okay. In the previous things, whatever we are discussing previously, okay, let me just yeah, we are having y is equal to a0 plus a1 x1 plus a2 x2 and so on. Here x1 x2 all are like fixed values kind of thing. But we may have scenario where this x1, x2 are not like a fixed thing. Rather, it is some kind of functions p0x, p1x, pnx. This is one scenario. We have data point x0, xi, and yi. Okay, but here this one x data points are not like constant values. They are some kind of functions. For example, in this case, P0x is like xi and the power law. P1x is like trigonometric function, this one Fourier series, sine of ix or cos of ix, whatever it is. Pnx is maybe exponential function. I am rewriting like y is equal to a0 x to power I plus a1 maybe sine of ix plus a2. Sorry, I'm not writing this one. This plus an exponential alpha ix. I'll do, I mean, this is scenario again. In this case, again, we'll follow the same process, whatever we are doing before. We'll just trying to linearize these equations. Once we linearize this equation, we'll solve for a0, a1, and an and put back into this equation. This is no issue with respect to that. But the problems comes where this coefficient is, which Dr. Raj also is referring, that power is variable. I am playing with the power actually. So let's say A is entering non-linearly in the expression for y of x. In that case, my sum of residual square will be given by yi minus y calculated xi square. So here I have to minimize, I have to use some kind of optimization technique, not the regression analysis. Okay, to do if A is entering into the equation non-linearly, that means A is not constant, A is variable. So these are some of the things which I wanted to mention about the linear regression. Okay, now how we can okay, here again I just sorry, this one, yeah. So here let me just, this one is done. Yes, I have done this part. I'll just skip that part. So this is all about the polynomial regression for different scenarios actually, where we are dealing with a linear or non-linear scenarios. Okay, where we have multiple data points. How do we deal with that thing? It's very easy actually. It's not that tough, but people try to go away from this. Rather, they will go for simple kind of tools. So till this point, I'll continue from this point onward. Till this point, anybody have any doubts, any queries?
Actually, it's going very wonderful. Actually, so
Okay.
I taught this course. I am teaching this course,
Yeah, this is very interesting course.
and see, after doing this thing, just to calculating R square data fitting.
Yes,
So
yes,
I
yes.
do the data fitting, but this R square calculations and all this, I don't teach students actually after doing my masters, because Pichumani sir taught all these things.
Dr. Pichwani, I knew.
Excellent.
You know,
So
uh,
so
uh,
now I thought I should also include this in my course notes. Actually, it's a good thing. Actually,
that's good. Actually, every time when even the research scholars, actually, my research scholars, they come with the data fitting and they tell us, sir, this is my R square value. So I asked them, what is this R square value? Tell me first, what do you understand from that actually? Then only we can understand the data. So this is the biggest problem with the analysis of the data actually. So we should not just leave the R square that, oh, my R square is 0.99. Let it over.
Yeah, actually, most of the time they take the Excel sheet and whatever fits, they just give that only, no?
If we don't know how it is being calculated, we cannot understand the meaning of that actually. That's the thing.
Yes, yes,
So
yes.
shall we proceed
Okay,
further?
continue. Yeah, yes, 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 continue. Thank you very much.
So now if I just go to another scenario, now this is completely different from regression analysis, what I'm just moving towards. Okay, this is about Newton's interpolation formula for polynomial interpolation. Okay, now this is something like, I mean, this Newton's interpolation formulas are used in lots of scenarios, not in the polynomial interpolation, but for the calculation of differential equation, calculation for integrals, calculation of finite difference methods, and all. There, all this Newton's forward difference, Newton's backward difference formulas are being used basically. But here we are utilizing the Newton's interpolation formula for our calculation in the case of this one in polynomial interpolation. The limitation of Newton's first we are talking Newton's forward difference formulation. Let's say the data is available to me like x0, x1, x2 till xn with corresponding y0, y1, y2 till yn. Okay, the problem here, not the problem, the limitation here is the x0 and x1, x1, x2, x2, x3, and xn minus 1 and xn should be equi-spaced, equidistant. This is the requirement of this data point. But if I see the most of the chemical engineering data points, okay, if I am measuring the viscosity of some lubricants, if I am dealing with this historical data point in a reactor, actually, none of the data is equispaced data point. They are non-equispaced data points. But let's talk about the equispaced data point first, then I'll go for the non-equispaced data point. So equispaced data point, let's say, I mean, this difference between this is delta x here, delta x here, delta x here, actually, delta x here, kind of thing, actually. Okay. So my general, I mean, let me divide it first to differences, then I'll come on to general equation. Okay. Let the first difference I define like delta yi, difference between the point yi plus 1 and yi minus 1, simply. Second difference, delta square yi, that is nothing but delta yi plus 1, and delta, I mean, that is something like delta yi plus 1 minus delta yi kind of thing. Okay, so if I just rearrange this equation with the help of this equation, then I obtain that delta square yi is equal to yi plus 2 minus 2yi plus 1 minus yi. Then similarly I do for delta cube yi, and then I obtain one general expression. That we should not go into too much details. So delta I by a is equal to delta I minus y, delta I minus 1 by a plus 1 minus delta I minus 1 by a. So that's the same thing actually which we are doing here. Okay. So let me define a parameter alpha is equal to x minus x0 delta. So this we should be careful now. Why we are careful? I'll talk about later on another method actually. Alpha is equal to x1 x0 delta x. Now let me expand y of x with considering x0 as base, x0 plus alpha delta x actually. I mean, if I just simply put alpha delta x here, this alpha value here, it will be same as x actually. Okay. So let me expand this y of x with base as x0. I obtain a0 plus a1 alpha. I mean, this is again we are assuming this kind of form will obtain a1 alpha plus a2 alpha square, a3 alpha q, and an alpha n. Okay. Now in this expression, if I put in this complete expression, if I put x0, because alpha is this one, alpha is defined x1 as x0 delta x. If I put x become x0, alpha becomes 0, so I just simply obtain with a0, that means y0. Simply y of x0 becomes here. If you see here, this y0 is nothing but y of x0, y at x0. So that is y0, so a0. Okay. because we had obtained this kind, we had assumed this kind of expanded form of this y of x. So I need to calculate the value of a0, a1, a2, a3, and an, so on. Similarly, if I put alpha equal to 1, so this is alpha is equal to 0. So this is alpha equal to 0. This is alpha is equal to 1. Alpha is equal to 2. Alpha is equal to n. If I put all the values into this particular expression, I obtain different values of y of x0, y of x plus delta x, y of x plus 2 delta x, y of x plus n delta x. So when we have done this thing, let me go back to the general relationship. Let me put back all these values of a0s, a0, and then a0, a1, a2, and an. We have this equation, we have this equation, we have this equation. We are solving all these equations. Like in the first equation, we have a1, a2, a0, all are zeros in this equation. Only a0 is present. So if I'll write it like this, sorry, this going back here. So a0, a1, a2, an. In the first equation, only a0 was present, so 1, and rest becomes 0, 0, 0, and 0. In the second equation, like a0, a1, a2, and an. Third equation, a0, 2a1, 2a2 is 2 square a2, 2 to power an. So like this, it is proceeding. So this is general. This kind of equation you obtain upon solving this equation for a0, a1, a2, and an, and putting back into the expanded form, we have this kind of expression. Okay, with, because we will truncate the series somewhere. We'll truncate the series somewhere. So when we're truncating the series somewhere, we have some remainders. So this is R is remainder. Okay, so we have this kind of remainder equation, which is given by this expression, where alpha value, we know that alpha is equal to x minus x0 divided by n. Okay, so alpha we know, this delta x to power n plus 1 y, n plus 1 factorial. Here y, this is nothing but d n plus 1 y divided by dx n plus 1. This expression. But this z is coming. This z is also like y is the function of z alpha, like this. What is the z value? Z varies from x0 and xn. So either we take x0 and xn, two limits of z. Okay. So when we finally analyze this expression, we have this equation. I'll tell you how this equation works actually. How we'll develop the polynomial from this expression. So y of x is equal to y0 plus alpha delta y0 plus alpha into alpha minus 1 by 2 factorial delta square y0, and so on till remainder. So because we are truncating the series. Similarly, we have defined alpha is equal to x1 x0 into this, and we solve this equation, and we define differences in the forward manner actually, and for the equi-space data point. Similarly, if we go for backward differences, so in that case we use reverse delta. Reverse delta y is equal to yi minus I minus 1. Sometimes people refer to as del actually, some people, but I'll just avoid that del actually because it will confuse sometimes. So the reverse delta yi. So we define again differences. Reverse delta square yi, reverse delta yi, we define the differences, and alpha value is not different. That's what I was saying. We should do x minus xn divided by delta x. So last point. So in case of forward differences, we have the first point x0, this one. But in this case, we have last point xn in the backward difference. Again, same equation. We have to find the value of a0s, a1, a2, and a3. And then putting back all these equations, I'm just analyzing the forward difference method. We obtain this expression. In this expression, this delta yn is nothing but this one, delta yi. Okay, the delta yi is equal to yi minus yi minus 1. So n, when I'm saying n means it is like yn minus yn minus 1. Or let me rewrite here. Delta yn is equal to yn minus 1. Okay, so this way actually we obtain all the differences, remainders, and all, and then put back into this equation, we get the polynomial. Just an example. Here, let's say I have this data point 1, 2, 3, and 4. You see, delta x here is 1, delta x here is 1, delta x here is 1. So equidistant data point. yi 7, 17, 53 and 157. So this is some kind of lubrication data somewhere we have taken. So here I wanted to make a model polynomial equation using Newton's forward difference method. Newton's forward difference method. What should I do? First, I take see delta x equal to 1. Then I calculate alpha. Alpha is equal to x minus x0 by delta x. So the x0 here is 1. X0 is because x0 is equal to 1. So x minus 1 we obtain, delta x is 1. So I obtain alpha is equal to x minus 1. Now I'll go back to my this equation, this one. Y0 plus alpha, delta y0 plus alpha into alpha minus 1 2 factorial delta square y0. Okay. So let me see how many deltas are appearing. First delta, delta y. Delta y is nothing but difference between these 2 points. Okay. 17 minus 7. 53 minus 17, 36. 157 minus 53 is 104. And then again taking difference of these two is my delta y, delta square yi. Then taking difference between these two, and then taking difference between delta cube y. So I have 3 delta y actually, so it will be some kind of cubic polynomial. We'll see how. So I put value of y0 into the y0 is my 7. This is y0, so this is 7. Alpha is x minus 1. So I'm not putting, let's first develop the polynomial in the form of alpha. This delta y0 is 10. This is delta y0. Delta y0 is 10. Delta square y0 is 26. That is 26. Delta q y0 is 42. So all these values are we have put here, and then rest in the alpha form. So if I solve this equation, or I can also do like alpha is equal to x minus 1, and this will be simply x minus 2, and this is x minus 1, x minus 2, x minus 3. So if I put all those, I can get a polynomial in the form of x also. But here I just simply retain y of x equal to 7 plus 11 alpha, 8 alpha square plus 8 alpha cube, alpha to power 3. So I just simply put 7 plus 11 to alpha, this one x minus 1 minus 8 x minus 1 square plus 8 x minus 1 cube. So I obtain the form into the x form. I will put what is the value of x in between 1 to 4. I'll get the value of y corresponding. So this way we have developed the model for the using Newton's forward difference method. Similarly, if I use the Newton's backward difference, now here I had already calculated all the backward differences. This is yn, this is again delta yn, this is delta square yn, this is delta cube yn. Or let me use different color to just mention this. Okay, so just simply this is my yn, delta yn, delta square yn, delta cube yn. Okay, this way actually, this data point. So let me reverse del actually, not delta, reverse del. So let me go back to the backward difference equation. Okay, and then putting all the values of alpha, delta, this is delta x is 1, xn is 4, and delta, so I obtain this alpha value here. Then putting back all the differences, delta yn square, reverse del square yn, and so on. And then we obtain, after putting all the values of that, see yn was 157, yn is 157. Okay, delta yn is 104. So I have 157, 104, 68, and 42, all those values, and then alpha. In this case, let me put this one, after solving this expression in the form of alpha, we obtain this equation, and in the form of x, we obtain 7x cubed minus 29x squared plus 48x minus 90. So y of x is equal to, we obtain this expression. Now, this is from the backward difference, that, and this one was from the forward difference. We can put the values of whatever we want. Between x 1 to 4, whatever the value we put, we'll get the value of y. So this is the polynomial. How do we develop between the for the available data point? Okay. Now let's say my data are non-equidistant, are not evenly spaced. Data are not evenly spaced. Okay. So that means this delta x0, delta x1, delta x2, delta xn. Okay, n minus 1 level, n minus 1. So all these delta x are different. Okay, data is not evenly spaced actually. Okay, so in that case, what do? We define different order of finite divided differences. This is something like, if data is available, like the zeroth order finite difference is nothing but y0, y of x0 is y0. First order finite difference is y of x1, x1 x0. So that is nothing but y1 minus y0 divided by x1 minus x0. Similarly, second order difference, if let's say y2 is there and x2 is there, so second order difference is considering x2, x1 and x0, and that is nothing but, let's say I've calculated divided difference for this one. Okay, this is like divided difference of y2 y1, and this is y1 y0. So y of x2 x1, y of x1 x0. So whatever I have calculated here and here, that value will come here, divided by x2 minus x0. If I'm doing third order, it will be like x3 by 3. So what are the differences I have calculated now? So that means that this difference, I have to calculate all over divided by x3 minus x0. I have to proceed like this actually. This is not third order actually, this is nth order. Nth order difference. Okay. So first we define the differences and then putting back into general equation actually. Or let's say rearranging this equation first before doing that. Let's say I'm rearranging this equation into other form, that is this this expression y of xn minus 1 to x0, nth order divided difference will be equal to yn divided by xn minus x0, xn minus 1 till xn minus 1 plus yn minus 1 divided by till xn minus 1 x1. So here xn minus 1 and xn minus 1 will not be there, xn minus 1, xn minus 2 plus y0. So we are doing the reverse order, y0 divided by x0 minus x1, x0 minus x2, x0 minus xn. So basically we have rearranged this expression. Okay, we have rearranged this expression so that nth order will result into this equation, yn plus yn minus 1 plus till y0. So all the summation of y's divided by the product of x, the difference between x values, but j should not be equal to I. 0 to n, j should not be equal to I. So we obtain this expression. So this is general expression we obtain for divided difference. So let me go back to the general equation. So if I'm putting back to general equation, I'll obtain this one. This is the equation which we have come up with this divided difference. So let me put this is my general equation. In this equation, let me put the divided difference here, divided difference here, divided difference here, with the help of this expression. Okay, so we don't have much time to discuss each and everything with this equation. Let me go to the final one. Okay, this one I think I did this earlier, not Lagrangian. Okay, let me just do this thing. Okay, so this divided difference, this is the only equation. We are not into the final equation here, but this is general equation. I'll have y0 plus x1 x0, y x1 x0, x minus x0 into x minus x1, y x2 x1 x0, and similarly so on till nth term. Okay, and then we'll put back all the differences here, and then we'll develop a polynomial. How do we apply that? Let's say here, let's say I have this this data point. This data point, what it says that delta x1 is equal to 3, delta x2 is equal to 2, delta x3 is equal to 1. So or it is unevenly spaced data point. Corresponding values of y's are mentioned here. Okay. First thing is I have to evaluate the divided differences. So that y0, this is y0. x1, x0 becomes, what I did, simply I did y1 minus y0 divided by x1 minus x0. So that is, this is my y1, this is my y0. Okay. Similarly here, this is y2, this is my y3. Okay, so here y2 minus y1 divided by x2 minus x1, y3 minus y2 divided by x3 minus x2, I obtain these expressions. So again, taking the difference between this and this, so what I did simply y0, sorry, y1 x2 x1 minus y0 in the square bracket x1 x0 divided by x2 minus x0. Okay, we have calculated all the differences. Once we have calculated this difference, this is again y0, this is again y0. So this value, and this value, I'll go back, put here, here, and the third point, whatever the third point is there, I'll put there actually. And you see here, x minus x0, x minus x0, x1 x1. So we'll do that like this now. Y0, this is my y0. X minus x0, x0 is 1. So this is nothing, x minus x0 into first divided difference, 0.4620. Plus, this is minus value. I just simply took minus so that we can difference. This is y x2, x1, x0, x minus 1, x minus 4. Plus this value into x minus 1 to x minus 1 to x minus 6. So this way we will solve this polynomial. Okay, I don't have that polynomial here actually. Though if I just simply multiply that this equation, I'll get again a polynomial in the form of, it will be something like y of x is equal to x cube, x square, x, and some coefficient. So this is for unevenly divided points, actually, or let's say not evenly divided or not evenly spaced points. So we are developing a polynomial for a evenly spaced point and not evenly spaced point. Okay. Now one more thing, with the help for this not evenly spaced point, another very important method which is typically followed is this Lagrange interpolation. This Lagrange interpolation, if you see, the general polynomial is same polynomial whatever we are discussing so far for Newton's forward, backward, Newton divided difference. Only the forms are different. Here a little bit difference here, a0, a1, a2, aj, and an are there actually. But the data points are, this is delta x0, delta x1, delta x2, and delta xn minus 1 are not evenly spaced data points. Okay. So here, let's say, this polynomial is there, Lagrange interpolation polynomial, but we don't know what is the value of a0, a1, a2, and an. So that value has to be found out. That how it is being found out? If I put simply in this expression x equal to x0, in this expression I put x equal to x0. If I put x equal to x0, wherever x0 minus x0, x0, that will be cancelled out, I obtain the first expression. If I put in this expression x equal to x1, I'll obtain this expression. Okay. Similarly, x equal to xj, and then after doing all this analysis and then putting back all those, let me this in this case a0 will be equal to y0 divided by x0 minus x1 till x0 minus xn. Similarly, a1 rearranging that equation. So rearranging this equation, you have obtained a1. Similarly, aj rearranged. Whatever a0, a1, aj will come, we will put back into this expression, and this kind of expression obtained. We can rearrange this expression like this one. You can see here the short form that expression, because here you see these are nothing but products, x products and x products into y0 plus products divided by products into y1. So we can just simply in the shorter form we can write like summation of all the y's, and within that product of x minus x divided by xj minus xi with I equal to 0 to n, xj equal to 0 to n. This region, this is being referred as Lagrange of the order of n. Lagrange interpolation of the order of n actually. Okay. Let's say implementing this Lagrange interpolation, how do we do that? I'm not talking about the big equation. I'm just focusing upon the smaller level. Let's say I have 3 data points. I have these 3 data points. I'm sorry, 4 data points. 4 data points, not 3 data. I wanted to develop a polynomial, and these all are non-equi-space points. So what I should do actually, I go back here. I considered it till x3, x minus x1, x minus x2, x1 and x3, and then truncate rest of the points. Okay, that's why this remainder is coming actually, because we are truncating this series. Okay, so when I'm doing that, y of x equal to x minus x1, x minus x2, x minus x3 divided by x0 minus x1, x0 minus x2, x0 minus x3 into y0 plus, now it's second term. So this was the first term, this comes from y0, now comes from y1 again. Only thing is my this one change, this numerator and denominator will change by x1 x0, x minus x2, x minus x3 divided by x1 minus x0, x1 minus x2, x1 minus x3, y1, and so on till y3, because we have y0, y1, y2 and y3 data point. So we have this, we solve this expression. When we solve this expression, we'll get a polynomial. Just an example, let's say I have this data point, all are non-evenly spaced data points. I want to estimate what will be the value at x is equal to 3. At x equal to 3, okay? And this data are not arranged. So I don't need to arrange the data. I can simply use the data as it is, because some methods are there which need data arrangement in the orders. I'm not doing that here. I'm just simply have to make a model. I have to make a model, and then from that model I can calculate the value of y at a particular x value. So what I do, I go back here, this expression, or I had already simplified expression here. I put the value of x1, x2, x3, x0, x1, x2, x0, x3, and y0, y1, y2, y3 into this expression I obtained. And x I said 3. So x is 3, 3, 3, 3, this is 3, this is 3, this is 3. So I'll put all the values and then simply solve this. This is my y0, you can see this is y0, this is y1, y1, this is y2, this is y3. So I just simply put all the x values, all the y values, straightforward, I obtain the value 20.21. If you see, remember in the beginning we have taken the same example where at x equal to 3 we have polynomial value 20.21 we obtain. So this is, you can say that this non-evenly spaced data point, how we can develop a polynomial and how we can use it actually. Okay, see the problem with the Lagrange interpolation is, let's say here only 4 data points are there. I have n number of data points. What degree of polynomial I should consider? What happens typically, if my degree of polynomial increases, there is oscillation in the results. Okay, or let's say degree is not increase, I'll simply say is high. If it is low, degree of polynomial is low actually, in that case there are inaccuracies in the results actually, inaccuracies in the results. So I have to decide what degree of polynomial I should take. Okay, so that is the question here. So that is being reduced into another method which we say Neville's method actually, which only consider first 2 terms, x1 and x2, y1 and y2 of this one. Let's say this data point. This only retain 2 data points only, and then reduce the whole equation, whole big equation into a linear kind of form. So this is some kind of linear equations they have converted into this method actually. Okay, so just to avoid the problem of oscillations, to avoid the problem of inaccuracies, which is the major issue with the Lagrange interpolation, what degree of polynomial we should consider if n number of data points are there, that Neville's methods take care. Okay, so that way actually we can analyze this data points. So I think I'll not go further into this different in this discussion.
So here in this Neville's one, you are considering only two data points.
Yes, yes. If you see here, I'll
So how would it
I'll,
take care all
I'll
the
go back.
rest of the
Okay.
trains actually?
See, I'll come on to it. I'll come on to it. Yeah, here. If I just go back here.
Yeah, this one only.
Yeah, yeah. So what we are doing actually, let's say let me put x equal to x1. Okay, if I put x equal to x1 here, let's say, okay, what this will
Hmm.
be cancelled out. Okay, I'll
Correct.
answer your point. If I put x equal to x2, this will be cancelled out, and I can rearrange this equation, and then it will be something like a linear kind of equation can be seen. Now, what your doubt? Consider your doubt. Let's say here I have this example. What we are doing? I'll tell you with respect to example. Actually, how do we are doing? Let's say these are the data points are available. Okay, and I want, you see there are 5 data points. There are 5 data points, and I want to have a solution at a particular, I want to have a model actually, so that I can get the solution at f is equal to 27.5. So 27.5 may be lying here, 27.5, and I want the solution at that particular point. Okay, so this 27.5 in this equation is nothing but this x is 27.5, and what we do actually, we go by one. In this method, one of the important thing is we have to rearrange the data points. And how do we rearrange data point? By seeing the closeness with respect to the data point. For example, I made this
So
paper.
you are practically the bracketing the root actually here,
Yes,
right?
yes, yes, yes. We are practically bracketing a root around the
Ah,
value.
that's fine then. That's fine.
Okay,
Yes.
so that way actually we proceed,
Hmm.
and this whole thing is we are developing this equation is nothing but the modified form of this equation only. How do we use? So we basically bracketing the roots, and then we calculating. We are developing this pi0, pi1, pi2, pi3, pi4 corresponding values. We are simply put into this particular equation, and we will see when the two values pi2 and pi, if you see pi1 0.4609, pi2 0.4620, pi3 0.46174, these three values are close to each other, but the pi4 is starting changing the value. So oscillation is going when we are going for further calculation. Actually, in this case pi4 is limited because we have 5 data points. Okay, but the data is value changing. So we see when two values are close to each other, we stop there. 0.46200 and 0.46174, they are close to each other basically. So let's say 0.46174 is my true answer in this particular case for f is equal to 27.5. So it is 0.46174 because the oscillation is starting after that. We should not consider the final value. Okay, so that way we proceed with this Neville's approach. Okay, so this is all from my side, so I'm not discussing further into this. So basically I started, let me summarize this talk here. I started with the linear interpolation by taking some small examples that if I'm doing the straight line fitting, then the polynomial fitting, power law fitting, exponential fitting, or let's say I have number of independent variables, or let's say I have my this one independent variables are not linear, rather they are also non-linear. They are function of Fourier series, power law, exponential. Okay, so how do we do the linear regression analysis actually? So that's what I all discussed here, how we can use different methodologies. Then we are discussed for polynomial interpolation 3 methods: forward, backward, and divided differences. Forward and backward limited to evenly spaced data point, and divided for the non evenly spaced data point. Similarly, Lagrange interpolation is applicable for the non evenly spaced data points, but it is related to very large kind of polynomial actually. So what we do, and Lagrange interpolation has disadvantage, like if the polynomial is too big, oscillations are there. If the polynomial is too small, let's say I taken the quadratic polynomial there actually, three terms only, three terms. So it will result in inaccuracy. So I should not go for. So that's why Neville has proposed this modified approach by which we are just considering two data points step by step. Not only two data points. Like for example, here, here. I mean, for this case, these two data points. For this case, these two data points. For this case, these two data points, and like this actually. And then solving for using this approach, and we get the solution. So Neville's approach is good in that term actually. It reduced the number of calculations as compared to Lagrange interpolation. So this is all from my side about this linear interpolation and polynomial interpolation. If anybody have any doubt, please let me.
Yeah. Actually, thank you very much. It was very much enthusiastic session. Actually, energy level was high from beginning. It was still, it is still high after 2 hours of the session also, and it went at a very, actually, I will say, interactive and fruitful way. I learned a lot, whatever I forgot to teach also
No,
over
no,
the period of time, because I was
we
teaching
all
something
learn
else.
from each other. We all learn from each other. It's not like
Yes.
I
So
also
now I
learn
thought
from you.
I should also add something in my teaching also, and it's good at least, and we learned something. So I would ask the means participants to ask some questions if they have from Dr. Vimal. Any question from participant sides they
I
can
think
ask?
people are getting exhausted 2 hour sessions.
No. It was really indeed. Actually, I didn't miss even a single thing. Actually,
Hello.
so yes, sir. Yes,
Yeah.
Dr. Jalesh.
Yeah. So, sir, can you please explain why the oscillations occurs when we increase the power of the interpolant?
Why the oscillations?
Oscillations.
See, this is one is I always tell the what see when we are taking the coefficient values actually. The
Yeah.
coefficient values there, what I mean, what values should we consider? I mean, what order rounding off? We are doing the rounding off into the coefficient values actually. So that creates, you can practice this with the help of Microsoft Excel. I'll tell you where what you take the simple data point and then do the this one regression, use different polynomial orders, and then just take this coefficient values and put into Excel. You can see yourself, if you increase the number of significant digits of the coefficients, it will make a huge impact. So one is that region. Other is we are always truncating somewhere we are truncating our series. So that truncation also leads into this error.
Okay.
So
Any
I'm
other question from participant sides?